already seen him. He is a PhD student in our department. So over to him.
Okay, thank you. And a few disclaimers before I start. So I just prepared the slides like last night, so beware of some goof ups. So, so in case I run out of say slides, I will switch to the whiteboard. But yeah, before we begin, you can see this 5 on the slide, and even I have to figure out what exactly did I mean when I placed it. So yeah, today is the 5th day of the summer school, and how it's going for you guys? Yeah, something, some reply. Good, bad, ugly. Good, really good. Doesn't seem so. Okay, so let's get started. I guess. Okay, so the title of the talk is, what is the title of the talk, by the way? Okay. So believing that, I hope the presentation won't be very chaotic. So, okay, so I guess it's just not the 5th day of the summer school, but it's something else. It's like a countdown. Oh, this is strange. I didn't expect this. Well, any guesses? What is the connection this has to do with the talk? Chaos? Okay, so who are these gentlemen? Oh, great. You guys are into movies, I guess. Okay, so Joker has something to do with chaos, right? And what is it? He's the self-claimed agent of chaos. And on the other hand, Batman is like, but complete chaos is impossible. To which Joker is like, what are you talking, freak? And Batman is, I can prove it. And that exactly is what we are going to do today. We are going to see that why complete chaos is impossible. But when I'm saying that complete chaos is impossible, maybe I'm talking in terms of more serious and mundane stuff. Being in IFC, we're not supposed to talk like the way Batman and Joker would be talking about. Maybe they are concerned about peace in the world, or maybe Gotham, or stuff like that. But we would be just sticking ourselves to, say, graphs and sequences and maybe arithmetic progressions, or at best, maybe some games of tic-tac-toe. Okay, so let's just start with the formal talk. Yeah, we are doing some serious stuff here. So what is it? We have a graph, say a complete graph. Let's take the Facebook. Facebook is a graph, right? Where two people are friends, then we put an edge between them. They can be friends, say I put a red colored edge. If they are not, say suppose I put a blue edge. Now, I want to make some claim that no matter whom you pick, no matter what group of 6 people you pick, maybe they are all friends, maybe none of them are friends, they're all strangers. It can be just anything, very arbitrary. But I'm claiming that there will exist a blue triangle or a red triangle. Have you guys seen this problem before? So it's like I have a graph, a complete graph with 6 vertices, and 2 people can be either friend or not, and it could be just arbitrary coloring of the edges. And I'm claiming that no matter how it is, there will always exist a red triangle or a blue triangle. Just like in this example, as you can see, there is a red triangle here, right? There's a coloring. There is a blue triangle as well, but I'm only asking you for either a red triangle or a blue triangle. What about some other colors? Okay, so this obviously has a blue triangle, but no red triangles. Fine, I'm fine with that. So is this one. This is like a complete red click. You guys know the term click, right? Click means a complete graph. Cool. This is another coloring. And again, this has, say, a red triangle. What about this coloring? Yeah, there's a blue triangle. So, is the claim clear? What I want to prove? That there will exist either a blue triangle or a red triangle. Or rather than always explicitly repeating myself that either a red triangle or a blue triangle, I will say I want a monochromatic triangle. Monochromatic, a triangle of one color. Okay? So any thoughts on how we are going to go ahead? How to prove this statement? Any thoughts? Yep. Yeah. Can you come up to the board and just explain? Will that be too much? Okay, the guy just behind you. Yeah, you can come. Sure. Are there markers? Yeah, there should be. Oh, we have red markers and blue markers. Thanks. Yes.
Suppose that this person has two friends. So if they are not interconnected,
Okay, I will hold this for you.
so if they are not interconnected, let's say कि they do not exist any triangle.
Okay, sure.
So they will have some other friend also.
Okay, cool.
So if they are not matlab there do not exist a triangle there, there must be a triangle here. So our assumption ki there must there do not exist a triangle between monochromatic triangle is wrong.
Yeah, but there could be a case like this is blue again and this is not a red triangle. Like, okay, you are close, kind of close, but it requires some more argument. Yeah, you can go ahead as well with that, no problem.
Some other edge would be there ki which has two same.
Okay, in spirit you're right. Okay, let's see what exactly, or rather how tight we can make our arguments. Let's see. So just observe. Okay, let's consider just one vertex, just like the way he did. Let's consider one vertex, and let's look into its neighbors. Like it can have some red neighbors, some blue neighbors, right? It could be just anything arbitrary. Maybe it has, by red neighbor I mean the edges incident to it may be red or blue. It could be anything arbitrary, right? There are 5 edges incident to it because it's a complete graph with 6 vertices. Sure? Now, just observe that how many red edges and how many blue edges can be there. What are the total possibilities? There could be like 5 red edges, like here, everyone is 5 and 0 blue. There could be 4 red and 1 blue, and 3 red and 2 blue, and 2 red and 1 blue, and similarly 1 red and 4 blue, and 0 red and 5 blue, right? So these are the total number of things. So the following statement is true, that at least 3 of the edges are either red or blue. Do you agree to that? At least 3. It could be red or blue. So let's consider this. This could have been, I'm not even claiming anything about this edge. This could be red or this could be blue. And when I'm saying red, there is an equivalent argument for blue as well. So what I'm saying is that at least 3 of the edges are of same color. Simple argument. Any doubts with this argument? No? Okay, great. So as an adversary, I will try to forbid any sort of monochromatic triangle. So what I'm going to do, I'm going to say, see this triangle, I'm going to see this triangle, and I'm going to see this triangle. I'm going to consider them one at a time. Okay, to forbid a red triangle, I have put a blue edge here. To forbid a red triangle over there, this triangle, I have put a blue edge here. And similarly, to forbid a red triangle, I'm going to put a blue edge there, and oops, my back's against the wall. I'm getting a blue triangle. And in order to avoid this, I have to put a red triangle, I have to put a red edge, and which will lead to a red triangle. Right? So this is a proof that if I have 6 vertices, there will always exist either a red triangle or a blue triangle. It's a simple thing, right? Any doubts? Okay, so what have we proved here? We have proved that with 6 vertices, we are getting this. But is it also true for, say, 7 vertices? No? Yes? How many yes? 2 yes. How many no? No, no. 0 no's. So what about the people who are neither yes nor no? Like, you are computing? Okay, the computation is going on. Great. Okay, so are you convinced that with 6 vertices, the statement is true, that you are always going to get a monochromatic triangle no matter how the coloring is? So I'm coloring it with red and blue, all the edges, mind you, and I want a monochromatic triangle. And with 6 vertices, here is the proof. The question is, what about 7 vertices? Is it true? Yes? Who's saying yes? Please raise their hands. Yes, you?
At least has a 6 vertex subgraph.
The coolest proof ever. I mean, you have 7 vertices, you just throw away one guy, do the same proof, prove it, and bring back that 7th guy, and you're done. Great. What's your name? Great, Naman. Okay, good. So with 7 vertices, it is true. What about 8 vertices, 9 vertices? The same argument, right? So for 6 or more, we will always get a monochromatic triangle. Great. But what about 5 vertices? What about 5 vertices? Will you be able to prove something? Anything? Yes? You think yes? You can find always find a monochromatic triangle? And what's your argument? Four or more vertices. So you mean to say that any graph, any complete graph with 4 vertices is always bound to have a monochromatic triangle, independent of how I color it? Okay. Just take some time, let's think, no rush. So you are claiming with 4 vertices it is true. Someone is nodding his head in negation. You? It is not true with 4 vertices? It's not true? And how do you argue that it's not true with 4? Okay, well I didn't get it exactly because it's a porous answer, yes? Exactly. So what are you doing? Basically, you are giving me an example, a coloring. You are providing me a counter example, a coloring for which it is not true. Because in order to prove it, you have to prove it for every coloring. And you are coming up with one coloring for which it doesn't work. Okay, so for 4, she has an example. And what is it? That, suppose these are my, and suppose this is a coloring, and what do you do with, this is what you meant? Okay, so for 4, we have a counter example. That means we know that no matter, I mean, we cannot guarantee a blue triangle or a red triangle. But what about 5? What about 5? If I add one more vertex, what about this? Any thoughts? So basically the strategy is clear, right? You have to come up with some coloring, and it might be a little exhaustive, and okay, maybe in the interest of time, maybe not, maybe I guess I have a lot of time and I want to kill it somehow. Okay, so this is an example. It's a little tilted, but the point is that it's a cycle of length 5. There's a red cycle and there's also a blue cycle inside. So the star is also a cycle, if you see. So what do we get out of this? That with 6 vertices, you can 6 or more, you can always guarantee that there exists a monochromatic triangle, but with 5 you can't. That means 6 is like a threshold. 6 is a limit for guaranteeing a monochromatic triangle. But there's nothing special about a triangle. Suppose if I ask the same question, that I want not just a triangle but any complete graph of size k. Okay? And I'm asking you that how large my host graph, like over here the host graph is of size 6, how large my host graph is required to be to ensure a monochromatic clique of size 6. Yeah, sorry. Can you be louder? By 2, just multiply it by 2. Divide by 2. What do you want to divide it by 2? I mean, what is divided by 2? Okay, so I'm asking you that I want, okay, let me write it. I want a monochromatic clique of size k. This is what I want. Okay. I'm asking you what is the size of the host clique. For k equals to 3, we saw that let it be n equals to 6. And someone is saying that for any value of k, we are going to divide it by 2 or do you multiply by 2? Okay, so here is a conjecture. Can you guys see it with the lights off on the board? You can't, so I would rather switch it on. Is it a problem? Is it a problem? You want to this way? Is it fine? Fine? Okay, okay. So n is equals to k twice k. This is a conjecture. Reasonable. For k equals to 3 it works. Maybe for other values of k also it should. Who knows? Sorry? It could be a k factorial. Okay, there's another conjecture that n is k factorial. Okay. Okay. Any other conjectures? How about 3 choose 2, like k choose 2? Even that fits in, isn't it? 3 choose 2, 3 into 2 by, or it doesn't. Yeah, it does. Yeah. Yes. Okay. Mm-hmm.
We want that no other same shape should exist. So I have to take a shape of K,
Mm-hmm.
and I have already chosen. So the remaining K minus 2 vertices
Mm-hmm.
that particular side
Okay.
should have different color, or they should not make that shape.
Okay, but where are you getting the remaining k minus 2? Like those are from the host graph, right? Yeah, yeah,
In this example, if you consider the compost line,
yeah, yeah,
here we have 2 vertices,
yeah,
and the K was 3.
yes,
2 is 1, so we have one vertex beyond that line,
okay,
and that should have something different to not to make that shape something other.
okay,
Something that should not make that shape. So for every line we have beyond it or after it k minus 2.
mm-hmm.
You have k lines in the shape. So
Okay, interesting line of thought, but I'm not sure whether I completely am getting it. Anyways, actually, a lot of people have tried to solve these things, even for like values of 4, 5, 6 smaller values. And what is this? Okay, so I'm really bad at plotting and stuff, but this is like a plot of the values that these are the values which are, so this is my k. Oh, it's really small, I'm sorry. So size of the monochromatic clique that we are asking for, and this is the size of the host clique, okay? And the values, okay, so there's a blue curve and there is a orange curve. And actually the blue one is denoting an upper bound and the lower bound is the orange one. So over for k equals to 3, we got it to be n equals to 6 as the upper bound, and the lower bound was, well, it was, you can consider it 5 or 6. So it depends on how you define the lower bound. So if you want to define that, what is the highest value for which it doesn't work? Like for 5, it didn't work. So in that sense, it's the lower bound is 5. Or if you wanted to say that, what is just the next higher value, that is 6. So in that sense, both lower bound and upper bound for k equals to 3 is 6. And for 4 it is 18. Sorry, there's no 3.5. There are no graphs with 3.5 edges. So for 4 it's 18. And 5 onwards, we actually do not know what is in between. I mean, there could be a gap. What is this gap, basically? So for k equals to 3, it was easy that for 6, we could prove that no matter how you color, you will always get it. And for 5, you have a coloring for which it doesn't work. But we are not so fortunate for higher values. And the gap keeps on increasing. And this is like for k equals to 10, up to k equals to 10. These are values and the gaps are really large. And what exactly is this gap? Let's try to think, what exactly is this gap? So this gap is of the upper bound and the lower bound, and what I mean by that is that when I'm saying it's a lower bound, it's basically that for some coloring it doesn't work, it didn't work, and for every coloring it works for the upper bound, right? So for k equals to 3, for 6 it worked, and for 5 it didn't. So this gray area wasn't there. But for general values of k, it might so happen that it's working for some value, and there is a lot of gaps, and you can prove for some coloring, for some value of n, for some size of the host graph, that there is some coloring that is not working. You're able to show, just like for 5 we were able to do it, right? So now we'll shift our gears a little bit and see that we'll see that how to prove these lower bounds. So what do I mean when I'm saying that I want to prove a lower bound? What does it mean? It means that I have to come up with some coloring out of all possible colorings of the host graph. So suppose the host graph has n vertices, and I'm looking for a monochromatic clique of size k. So it's a sort of a game between n and k. Okay, we are playing some sort of a game. So how many edges are there in total in the host graph? It has n vertices. NC2? Right. How many colorings are possible of this host graph? Sorry? Yes? Exactly, 2 to the power NC2. Simple to see. For every edge, I have 2 options. Either I color it red or blue, and I keep on doing it for all edges. So it's 2 to the power n choose 2. Cool. Okay, so now, what am I going to do now? Okay, so for proving the existence of a coloring, what we are going to do is, we're going to use a little bit of probability. It's not very difficult probability, it's very easy. I mean, even if you are scared of probability like I was in my undergrads, no problem. All you need to just know is that when I say that probability of an event E is 1, that means it's a sure event. It's a sure event. And when I say that probability of E is less than 1, that means it's not. I mean, if the event is that today you are going to go for a dinner date and it is less than 1, that means chances are that you might not go. Okay? So this is important. Just keep in mind that the probability of the event is less than 1. So I am going to somehow say randomly color my host graph, and I'm going to see, I'm going to make sure that the probability is less than 1. That's all I'm going to do. So what is randomness here? I have just a complete graph of size n, and I'm just randomly, see, suppose this is my complete graph of size n. Well, this is the slide that I'm most proud of in this entire presentation. So this is a complete graph, and I'm going to do a random experiment with just an unbiased coin. So if the coin, I toss the coin, if it's head, then I color it with red, and if it's tail, I color it with blue. That's simple, there's nothing in it. Okay? And I want to make sure that the probability of the event, my favorable event, what is favorable event over here? The event is that I color it and I want there to exist a monochromatic clique of size k for some fixed value of k. Yep, there's it. There exists a monochromatic clique of size k This is my event, and if I can show that the probability is less than 1, that means it might not happen sometimes. Okay. Now, it's the same way of writing this thing. These two statements are same, right? Right? Or maybe wrong. That there exists a monochromatic clique of size k. Okay, I'm sorry. So I haven't defined what A is. A is any subset of the vertex set of the host graph, any subset of vertices whose size is k, and A is monochromatic. So I'm taking, so my, this small event, this event is that A is a subset of the vertex set, and that graph, that small graph on A, which is of size k, is monochromatic. And if it is true for some A, when I'm saying a union of events, that means out of all the events, even if one is true, I am done. So these two statements are equivalent. Any confusion with that? No? Maybe it's embarrassingly simple, that's why you aren't responding. Is it? So these two statements are equivalent, right? Okay, so have you heard of union bound? No? Okay, it's just a pompous way of just saying the Venn diagram. So in Venn diagrams, what do we know? That we have some events. We have like, say we have some events, and we say that the area of the union of these, say, circles, the union is less than equals to the sum of the area. We know this, right? We know this? Okay, cool. The same thing is over here. So instead of thinking in terms of probability, we can think in terms of the area of the objects. So each object is representing an event, and its area is precisely the probability of that event. So we started with what? We started with our favorable event that there exists some monochromatic clique of size k, and we are considering all possible subsets of size k, and we are taking a union over it. And then with this Venn diagram thing, I am writing this sort of an inequality because it is easier to deal with these individual stuff. This A is monochromatic. So A is some subset of size k of the host graph, and that is monochromatic. What is the probability of that? This is true? No? Yes? This is true, right? And as red and blue are like symmetric, so the probability that A is red is same as blue, so it is twice of this thing. Okay, so what is A is this red? So, okay, in the, maybe this is very simple to see that the probability that A is red is half to the power k choose 2. Simple? So, probability that A is monochromatic is just twice of this thing. Are you okay with this? So now, back to this inequality, we have that the probability that our favorable event is at most this a little weird looking expression. So this n choose k is coming from where? Okay, from this thing. This summation is giving us this n choose k. And this 2 is coming up from where? Exactly, and this is the probability that A is red or blue. Okay, so now this is maybe a little pedantic to you, but this is just a sort of an approximation that we do in order to get rid of these mind-boggling binomial coefficients. So over here we have done a simple thing. We have just used something what we call as the Stirling approximation, and we have written n choose k as n to the power k by k factorial. So this is greater than, say, this guy, and we have just split this thing, this twice into half to the power k choose 2 over here. And we have done this because it is quite easy to see that this left hand side is less than 1. Why? Because there are k by 2 plus 1 many 2's. So it's like 2 into 2 into 2 up to k by 2 plus 1 terms, and there in the denominator it's k factorial. So obviously even the number of terms is more in the denominator, and moreover the terms are quite more than 2 for like higher values of k. So this is clearly less than 1. Now what about this guy? So this is the decider. This is what is deciding, and the game that we started playing with k and n is going to be decided by this guy. So if n is less than 2 to the power k by 2, that means what? Okay, that means we are done. We are able to prove that this is less than 1. Right? So what did we get here? We got that n is less than 2 to the power k by 2. So as long as I can ensure that for a fixed k, I can ensure that n is less than 2 to the power k by 2, that means I will always find a coloring for which it doesn't work. And I'm not giving you an explicit coloring, I'm just saying that there exists something. So this is typically called an existential proof. I'm not constructing the coloring for you. There exists somewhere there. I can tell you just using simple probability. So, okay, so that's it for this graph stuff. I guess I have, how much time is left here? It's 11 now, or 12, yeah. 5 minutes more? 10 minutes more? Oh, that's a lot of time. Actually don't have that much material. Okay, so cool. So what did we see? We saw that, just to sort of summarize so far, that we are looking for a monochromatic clique of size k, and we are asking that how big our host graph is required to be in order to ensure that, no matter how you color it. So coming back to the title, that complete chaos is impossible. So what it means is that no matter how arbitrary your structure is, there is some regular structure inside it. Or putting it other way around, that if you want to find a regular structure of, say, some size of something, somehow you are able to measure it, some size k, then there is a finite, maybe no matter how large it is, there is some finite structure which might be very arbitrary. And by arbitrary, over in this context, it's like the arbitrary coloring it. Okay, so far, maybe, I don't know if Batman tells this to Joker, maybe he's convinced or maybe he's not. But jokes apart, in the real life, this guy was the Batman. So he proved, maybe sometime in the 20s, that that for any graph like this complete, so whatever I said actually was proved by him sometime back in the 20s. So this is Frank P. Ramsey. He was a British, I guess he was a logician, he was a lawyer, he was a mathematician, and he did all this wonderful stuff, and he didn't even live long enough to see his 27th birthday. So, okay, so what I said was for the complete graphs, and actually this can be proved for any graph. It's not just for the complete graphs, and not just graphs, it's also true for hypergraphs. Have you heard of hypergraphs? Like, if there are planes, there are hyperplanes, there are graphs, there are hypergraphs, there should be something. Okay, so hypergraphs are nothing, but, okay, for graphs, what do we have? We have a vertex set and we have an edge set, right? And a vertex set is typically just a set, it's a very boring set, nothing else is there, right? So in hypergraph, what you can have, the edges, a particular edge, say E, need not be, say, between just U and V, but there could be U, V, W, and whatever. So essentially, my edge set is a subset of the power set of V. That's it. This is how simple, horribly simple hypergraph is. And he proved that even for hypergraph, you can prove these things. Okay, so maybe in the remaining time, there's a quiz question for you. So we saw this in the context of graphs. This is also true, you say, in context of, say, point sets. Okay, let's pose the question first. So the question is that there are given some points in the plane, and we are asking, okay, we are asking the following question. So suppose I have some points in the plane. It's visible, right? No? Okay. And I'm interested in having, say, some convex sized polygons. I'm not sure whether this is something like this. Okay, so I have some points and I'm just arbitrarily making some polygons. Now the question is that if I want a quadrilateral of say size 4, so this is my quadrilateral k equals to 4, what is the size of the point set that will always ensure its existence? So obviously it should be at least 4. I mean, you can't do it with 3 points, right? Huh? So what I'm saying, just to repeat myself, that I am looking for a convex polygon of size 4 in a point set. And the point set is totally arbitrary, just like the coloring of the graphs. So I want a four-gun or a quadrilateral, and I'm asking you, what is the size of the host point set such that we will always find a quadrilateral? Greater than or equals to 4? Okay, I want something better than that, a more complete answer. Okay, for 4, is it true that you will always ensure with 4 points? Why no? Is there a counterexample? Great. What about say 5? You can, but it requires a proof. Will you be able to prove it? Anyone? So I think I have 2 more minutes. Anyone in 2 minutes? Yes? Sorry? Yeah? There are chances? Yes? You can come? Yes, please. No problem.
Okay, so we probably take 4 points and then add 1 point to it. We can say that.
Okay, sure. Yeah.
So this is a setting where we don't have a convex.
Right.
So if we try and place another point, let's say we place it outside this triangle, we'll always get
Okay.
polygon, right? We have it here. But if we say place it inside the triangle, if we place it on, we'll either place it on this side or this side. Then
So you have placed the remaining 2 points inside the triangle?
I'm just trying to consider the possibility.
Yeah, exactly. So what are the possibilities? Let's be very clear.
I can either place it outside the triangle.
This is one possibility.
Yeah.
And there are 2 points other than the triangle points, right? So you are talking about with 5 points.
Yeah.
So you have made a triangle out of 3 points, and there are 2 other remaining points.
I'm trying to add a point.
Sure. Yeah. So where are you adding it?
Suppose I'm adding it outside.
Okay.
Then I can always ensure a convex quadrilateral.
Okay. Great. Yeah. This is.
And if I just divide this plane into 2 parts about this point,
Okay.
then if I place it in, let's say I'm placing it inside.
Mhm.
So if I place it on this side, then I can just join these. Probably I can't. Okay. Let's do it this way. So let's divide this area into 3 parts. And then I'm just trying to say that if we place it in one of the parts, we can always ensure for the other points that it can
Okay.
be.
With the 5th point, yeah.
Yeah.
You're actually very close. So you can show that if you are placing in, say, suppose in this area, then actually
We can
this
make it
is
this
forming a thing.
And if we place it, we can.
So it depends on, okay, so when you are placing it, so there are 3 parts to this triangle, and depending on where you place it, you are going to get a quadrilateral with the other things.
Other things.
I mean, by things I mean with these points. There's a base, and there's a center one, and the 5th one. Okay, yeah, it's okay. It can definitely ensure you the gift. What's your name? Okay, sure. Just note it down. Oh yeah, thanks. So I guess that's all I have. Yep. And for references, actually I didn't prepare, so you can mail me or you can just search for Ramsey theory. It's like a huge, enormous theory in combinatorics, which is part of math, and there are really some nice, cute results. So yeah, thanks.
Let's thanks the speaker. So questions.